Ladies and gentlemen, mathematics was born in Greece more than 2,000 years ago. The modern mathematics that we learned and work with nowadays is reborn in Europe after the Enlightenment. In the 20th century, mathematics was undergoing big development in America. In the 21st century, we have many reasons to believe that mathematics will flourish in Asia as other part of the world. The success of this conference, so perfectly numbered, with almost 1,000 participants, most of them so young, in particular Professor Kim, must believe that our hope is grounded. That is why I'm so happy to deliver this talk as a token of appreciation to our colleague, Korean mathematicians, as well as the city of Busan, for welcoming us to this so beautiful city. Okay, so let me talk about mathematics. My title is deliberate provocative. Usually there's not so much a connection between arithmetic and integrable systems that are objects coming from mathematical physics. But I hope to point out that there is very deep connection between them. So let me start by talking about system of congruence equations, the object that we study in arithmetic every day. It's basically a system of polynomial equations with n variables. And so P1, Pm are polynomials with coefficient in Fp. Fp is the finite fields of numbers, congruence P number classes. And so we are interested in the number of solutions of these systems in Fp. And this is finite number. And more generally, we are interested in the number of solutions in some called fin extension, Fp to the R. So in algebraic geometries, we use more fancy languages. Instead of that system equation, we are talking about some algebraic varieties. So this is basically another way to write the system equation. Look at this ring of F, of polynomial rings modeled out by this ideal generated by polynomials P1, Pm. And in the algebraic geometry language, the set of solutions become the set of points of the algebraic varieties. So X, the Fp point of X is the set of solutions in the finite fields Fp. So solving equations is equivalent to finding points in algebraic varieties. So it's very and it's a clever operation to not to look in only a solution in one particular field, but finite field, but putting all together in a systems, so that you can talk about a solution in the algebraic closure of Fp, right? And the solution in the for congruence equation may not exist, but if you look at solution in algebraic closure field, they already exist, as long as you don't have too many equations. So there's a way to recover Fp point, so solution in some particular finite fields, form the solution in the algebraic closure by using the Galois groups. So Galois groups is a finite field is very simple. It is topologically generated by the Frobenius element, raising x to the power sp. And as you all know, the fixed point of the Frobenius is just the finite fields that we start with. So that is more or less obvious that when you're looking at the fixed point of the Frobenius, acting on the point of the x in Fp bar, you get back to the finite set of solutions in Fp that we start with. So instead of working with finite set, I bet the shape looking some infinite set, but much more geometric, because solution of in some algebraic closed fields that you can think about as just some solution, some complex numbers more or less, and in order to recover the set of solution in finite field, it just becomes a set of some fixed point of some of operators, Fourier operators that exist only in characteristic P. So thinking about fixed solutions as fixed point, some operators lead us to analogy with a very important formula in topology, it's called Lefschetz fixed point formula, and it has been one of the major motivations to develop algebraic geometries, to develop homology theory of algebraic varieties over finite fields, so that the Lefschetz fixed point formula can make sense. So that was one of the huge achievements of Grothendieck and his school. He was able to define L-adic vector space, so L with some prime numbers different from P. So he can define this finite dimensional L-adic vector space attached to any algebraic varieties. So HI, for short, I just denote HIX, the L-adic homology of X extended to FP bar, and we will use this compactly supported variant, so HIC. I will not extend into these details, but for fixed point formula, it's better to use HIC, so the homology compact support. And he proved this really magnificent Lefschetz formula. So that express the fixed point of Frobenius on the FP bar point algebraic varieties. So this is the set of solution equations that we are looking at, the set of congruence equations. So the number of fixed points can be expressed as a sum, alternating sum of traces of Frobenius acting on compactly support the homology of algebraic varieties. And this formula holds for, in absolute generality, holds for any algebraic variety of characteristic P. And later, Deligne proved a statement that is known for the last Weil conjectures. He proved that if you choose an isomorphism between the algebraic closure of L-adic numbers with C, field of complex numbers, and if alpha is any eigenvalue of the Frobenius acting on HIC, on the ith homology group with compact support, then when you transpose alpha to the complex numbers, then you get the inequality about this modulus. So that was one of the theorems that was one of the most beautiful theorem in algebraic geometries that we know, and it's being used almost every day in algebraic geometry and number theory. So in particular, these inequalities allow you to get an estimate about these numbers. But we are not so much concerned by estimating to have prove inequalities. We are more interested in some other problem. We are to try to prove some kind of equalities. So given some x prime, some algebraic varieties, that for other reasons, we believe that they should have the same number of points. So two different systems of congruence equation should have the same number of solutions. Of course, it's not true in general, but there's many cases this is true and it's not so easy to prove. So I am interested in these problems. So in many interesting cases, there's no way to prove it directly. I mean, you cannot make a map from X to X prime. There is no correspondence. But many cases you can prove this by using I use a metaphor of analytic continuation of equalities. That means that if we have two maps, so now instead of one single algebraic variety, we are considering a family of algebraic varieties. So now f is a map from x to y, f prime is a map from x prime to y. And the principle is that if you have these equalities of points in fibers for every point in the dense open subset of y, then we hope to continue this equality to hold y, right? That is kind of the framework. Of course, this is not true in general. It's true in very few cases. But we try to find conditions, particular geometric conditions on this map to make this principle work. So that is the purpose of my talk. So I will try to find applicable geometric conditions on the map f and f prime, so that if you have equalities of numbers of points on almost every fibers, then you can extend it to other fibers. So one of the main tools is, of course, the theory of Algebraic homologies. So we have this quite elaborate object called complex of sheaves, Arabic sheaf. I'm not going to define what it is, but it's just some gadget that knows about all the homology group of the fibers. So if you take this sheaf, this complex of sheaf, take its fibers at some point y, and take it HI group of homology, and any complex have homology groups, then you get back to the I's compactly support homology group of the fibers. So the point is that you want to understand, to provide assumption, to determine condition on F, so that you have good control on this complex of sheaf. So that's what I am going to set out to do this my talk. So let me start with simplest case. I mean, you cannot make it more simple. Let's look at the case of, perfect situation when the two maps are proper and smooth. X, F, and so all the fibers are smooth and proper algebraic varieties. And assume that there is this dense open subset of y such that you have equalities of numbers in the fibers of F and F prime. Then I claim in this case we can extend this equality to other fibers as well. So the reason is as for the following. The fact that the maps are proper and smooth imply that the cohomology of the complex sheaf, all this cohomology group of the fibers behave very nicely. They just form a local system. So there is no big chain, so to speak. It's very smooth, and the Deligne theorems, from using the estimate of Grothendieck of the trace of the eigenvalue of Frobenius, you can see that the number of points here imply that individually on HI we have the same trace on both sides. So that we have to use the estimate of the eigenvalue of Frobenius, because the eigenvalues can be separated by the absolute values. And then the Chebotarev theorem. Chebotarev theorem tell you that actually the knowledge of these equalities imply that the local systems themselves are isomorphic. And local systems are basically determined by respect to any dense open subset. So that we have this principle of analytic continuation equalities when the geometry is very, very nice, the proper and smooth map. So that is the very present situation, but in practice, it's not so much used. I mean, in some case, I know at least one example where from this you can prove some non-trivial inequalities, but usually you cannot. You really need to allow f and f prime to develop singularities if you want to prove some interesting equalities. So let's talking about singularities. So as I had to drop these smoothness assumptions. So now let me go forward. Now it's really 20th century mathematics. I mean, the 80s, Goreski and Macpherson developed this theory of perverse sheaves that is extremely efficient in dealing with singularities of algebraic maps. So I mean, in my talk, this is the most difficult, theoretic object to be grasped. So from this theory of perverse sheaf, there is Abel theory of perverse sheaf that play a substitute of the Newton sheaf for singular varieties. And in particular, we can define, instead of the HI that I've been talking about in the case of smooth and proper map, I can define the PHI that is a perverse sheaf. Okay, this as it's just a usual sheaf in the similar way to the usual homologies, but these objects are PHI are very complicated, but for some many they are more convenient to work with. So now let me go back to the Deligne theorem about vacant riches. So one can reformulate his theorem in the following situation: if F is a proper map, so now you allow the fibers of F to develop singularities, but I assume the source, the algebraic value F is smooth. Then, according to Deligne, this complex of sheaf F lower sheaf of QL is pure complex of sheaf. So this is very deep theorem, but it's not easy to grasp the meaning of this of the purity. But to let me explain how we can use it in practice to prove some numerical things. So one important consequence of purity is that it is semi-simple. That means this PHI is a really complicated object is direct sum of simple perverse sheaf. So that doesn't say much. Instead, I mean, nobody know, and except specialists, nobody know what it means. So, but let me just go further. So that if you can write, I mean, just do it even theoretically, you can write this complex of sheaf as a huge direct sum of indexed by alpha. K alpha is simple perverse sheaf, and they need to be shifted because they have different convolutional degrees. So we have this huge direct sum, and we are trying to study these decompositions. So this semi-simplicity theorem is very useful because we know exactly how to describe simple perverse sheaves, at least some way. So this is this simple perverse sheaf. So let Y is some even base, and we have a closed subscheme Z, open subscheme U of Z, and then we get an L irreducible local system on U. And then we define K to be some extension of L. So the I star is very easy to extension by 0. So this object live on Z, on this closed subscheme. But this functor of J, the intermediate extension functors, lower strict, lower star, is very complicated. So that is inconvenience. But according to Goreski-Macpherson, all simple perverse sheaves had to have these forms. So some kind of extension, complicated extension from a simple local systems. And I have no mean to define these functors of mean-intermediate extensions. But what really matters to us is that this simple perverse sheaf is completely determined by these local systems. So for us, what really matters is K is completely determined by L, or even by the restriction of L to any non-empty open subset of Z, as small as you wish. So that is somehow the topological root of this analytical continuation principle. So simple perverse sheaf can be determined by when you restrict it to a small set as you wish. And now we make a very important definition for us. If you have K as simple perverse sheaf, it makes sense to define support. The support of K is this closed subscheme Z, right? So we have, remember, we have this Z, and where K leaves, and K is 0 away from Z. So for every simple perverse sheaf, you can define support is some closed subscheme of algebraic varieties. And now if you have any map, F from X to Y and proper map, assume X to be smooth to get the purity, and you get this decomposition that I mentioned. I define the support of F is the support of all the simple constituent that we get in decompositions, right? And this is very important topological invariant of this algebraic map, because this Z alpha is precisely the locus where the topology of algebraic map undergoes some kind of very radical change, right? So the point is how to calculate this support F in general. It's quite close to these characteristic varieties in D model, but it's not quite. I mean, it's similar, but it's not the same. So this is very useful for analytic continuation principle, because if you assume that there are only full support, that means that only in this subfinite subset there is only Y. Then just by then you know that these complexes of sheaf are determined by its restriction to any open subset as small as you wish. And so if you know the equalities of number of points in almost everywhere, I mean in some dense open subset, then can today extend it into singular fibers, and that we are looking for. This is true, for example, in this obvious case when F is proper and smooth. But the question is, are there more interesting cases? In which case we can prove this support of F has full support, so to speak. And I mean, because this is analytic principle of analytic continuation is very strong, you expect this to be quite difficult to prove. I mean, it can be difficult to calculate the support of F in general. So we want to start with to list some case where you can prove this. So the first case is called the small map of Goreski-Macpherson. So small map is can be defined very quickly by these conditions. That when you move, you do the square of X over Y and remove the diagonals, and the dimension drops. So that is a map that is generically finite. At some point, they develop some fiber with dimensions, but when it does, the codimension of the locus must be very small, to speak. So in this case, Goreski-Macpherson proved that direct image is just single simple perverse sheaf that can be intermediate extension of just residue to any open subset. So it worked in this very particular case. And this is actually very useful in a representation theory. I mean, in modern representation theory Lie groups, the case of small map is very prominent. So this time I attempt to give some proof in a plenary talk for the first time in my life. So I guess you will not suffer too much. But let me just say that in this case, the main point of the Goretsky-Macpherson argument is to play the Poincare dualities against the convergent amplitude. Okay, so I will not do it further, but I will try to explain it in another case. Right? So the cache phrase is play Poincare dualities against convergent amplitudes, and we try to play this in another situation. So let's study another situation, somehow simpler, but let's study a relative curve, so a family of curves, right? This is we only assume that X is smooth when F is proper, a relative dimension 1, and we assume that generically the fiber is smooth, and we also assume this peculiar condition that the fibers are irreducible. So this is very important to prove the support theorem that the fibers are irreducible. And then this Goretsky-Macpherson also proved that the support of F is Y, the own support. And this calculation is very important in my work. So let me explain this. And again, this argument is to play Poincare dualities against convergent amplitude. So let me I try to explain this argument. I think it's very simple and very elegant. So I try to prove it. So let us assume that dimension of Y is 1. So the base is one-dimensional, and the space is two-dimensional. So of course the fibers are one-dimensional. And not to be confused, you better to shift by 2, right? And then by some convergent amplitude, we know that this HI vanish unless I is -2, -1, and 0, because the convergence of a curve have to be either to give 0, 1, or 2. So that is the first point. Okay. Let's assume we have a simple perverse sheaf of this direct factor of this, and assume that it has punctual support with dimension 0, right? So support Z alpha dimension 0, and then A0 which is non-zero, and so this proved by the common amplitude that A alpha had to be positive. That's the first point. So that is what we derive from convergent amplitude, that the N alpha, then the N alpha, that the sheaf had to be positive. But by Poincare dualities, if K alpha occurs, then K alpha dual and negative alpha also occurs. And K alpha check has same support as K alpha. And then this proves that N alpha is negative. Right? Okay. It follows that N alpha has to be 0. But then you also run into contradictions, because this has to be the direct factor of H2 of F star Qn. So that is called the top homology of the relative curve. That we know is just a constant sheaf, and that cannot have any direct factors of punctual support. So now the irreducibilities of the fibers prove that this thing is not possible. There can be no K alpha of support dimension 0 support, and thus the support of F had to be the full Y. So that is a very simple topological argument, but that proves a rather strong statement in this curve case. So now if you try to generalize in very general situation this Goretsky-Macpherson argument, So we get some nice things. It's not strong enough, but it's very nice. So if any map, proper maps, and if Z is a support of some simple perverse constituent, then you have this. The codimension of Z can be no greater than the dimension of the fibers, right? And moreover, if we know that geometric fibers are irreducible, then the codimension of Z has to be strictly less than the dimension of the fibers, right? In the case of curve, D is 1, and this means that codimension of Z has to be 0, and Z has to be the whole curve. But in general, you can only say that the codimension is no greater than the dimension of the fibers. And that does not allow us to calculate the support. But in some case, you can develop this argument so that you can do it. So the point is that for these so-called abelian fibrations, another name for the integrable systems, you can improve these Gorensky-Marfan inequalities just to prove the full support theorem. So let me explain what this abelian fibration is. So integrable system is in physics when you have some complex varieties, for example, with symplectic forms, and it is called integrable system if you can have as many as possible functions which are Poisson commuted, so called the first integrals. And in that case, there is called Hamiltonian actions on the fibers. So they look more or less like a torus. And so we have a system with a lot of torus, but then can have developed singularities. So in algebraic geometries, we just call it some abelian scheme, degeneration abelian scheme. So it's basically the same. But we need a bit more. So I will develop my own axiom of what should be abelian fibrations. So we have this abelian fibration is a proper map from M to S, and we also given some smooth commutative group scheme acting on M. So we separate our two objects, the proper map and some kind of smooth scheme acting on that proper map, and in both have relative dimension D. So we have to understand that generically P acts simply transitively on M. But you don't need to put it right now. So what is very important to assume is affine stabilizers. That means if you have any point M in M over S, then the stabilizer P has to be affine. Right? You do not allow some abelian varieties act trivially. Because that is not the serious assumption, because unless you do something really dumb, you never get abelian varieties in the stabilizers. But I need to make a much more serious assumptions, because the Tate model of P is polarizable. So that is not visible in topological explainabilities. But also this, usually, in many situations, this can be satisfied. So let me deep further into these geometric pictures. So P is a group scheme over S. So I assume have connected fibers. So therefore, every S in S, PS is a connected commutative groups, and according to Chevrolet, have canonical structures, has extension of abelian varieties by affine commutative groups, and this induced. This is a geometric object, and it's very useful to think about the linear object, the Tate models. So we have just the exact sequence of QL vector space of P extension of Tate model of A by Tate model of R. So many times, instead of working with P, we rather use these Tate models. It's much easier. As you will see. And the Tate model can be put together into a single object that's called the Tate model of P. So technically, it's a last homology of G of groups. And we have this erratic sheaf. These are local systems, that interpolate on the Tate modules. And now what I mean by polarizations is alternating forms on this periodic sheaf so that it is vanished on the Fi part and induces perfect pairing on the abelian part. So all this look very technical, but in practice it is not difficult to do this. I mean, in practice this is just called the wave pairings when you're working with but basically all this stuff means that you're really working in the framework of algebraic abelian fibrations. When you move to topological, then you can no longer define this kind of pairings. Okay. So now let me move to the how we can define, measure the singularities in the integrable systems. So there are many ways to do it, but algebraically there is the most basic and most easiest measure called delta invariant, because that is the same as delta invariant. That's certified for singular curve. So this is, you see, generically P is an abelian varieties, so that there is no R. So generically the dimension of R is 0. So that is for the nice fibers, the dimension of the phi part of P is 0. So I just define the invariant delta to be the dimension of the phi part in P. So very rough invariant, but just it will be enough for our purpose. And so I go to stratify the bases. So I have indeed S is the base of the abelian fibrations. Or for every delta, every integers, let me denote S delta to be the set of point S, so that delta of S is delta. And it happens to be a locally closed subscheme of S. And for example, for delta equal to 0, this is open subscheme of S. And here I had to make some conditions that P to S is called delta regular if the codim of S delta is greater than delta at least. What does it mean? So let's take delta equal to 1. If delta to 1, that means that S delta is codimensional greater than 1. So that means that S0 is non-empty. So this condition for delta equal to 1 just means that P is uniquely an abelian varieties. So there is some part it is smooth, and then you have to move on. So every time delta grows, the dimension have to drop at least 1. What happens is this condition is very natural. If you are working over complex numbers with the general Hamiltonian and complete integrable system, then you can prove this. This is not totally obvious, but you can prove it using the symplectic forms. You can prove these inequalities for any Hamiltonian integrable systems. But unfortunately, of characteristic P, the argument doesn't work, and have to. At least I don't know how to prove it characteristic P in general. I have to prove it by case in a very unpleasant way. But usually you can prove it. So I expect in many cases this should have to be true, but I just don't know how to prove it in general, except by some very unpleasant way. So but should assume that just looking for delta regular abelian fibration from now on and ignore the fibers that are not delta regular. So that is the main thing I want to talk about. Let's consider a delta regular abelian fibrations. That means have a proper map and a smooth group scheme acting on M, and I assume the delta regularities of P. So that means that at least the P this has to be generically an abelian varieties, and they have to come kind of degenerations. And assume M is smooth and the fiber is irreducible, then I can prove that support of F is S. So we have full support theorem. So the geometric condition here is just integrable systems, and with the one more regularities conditions. So the corollary. So if you have two integrable systems as above, so have over the same basis, and assume that genetic fibers P and P prime are isogenic abelian varieties. So we have two isogenous abelian scheme that degenerate in some way, satisfy the same conditions. And then this what happens, that you can prove the fibers as singular as can be still have same number of points by these principles. But the remark in practice, you cannot assume this MS irreducible and PS is connected. And when you have a degenerate abelian varieties, it always acquires some connected component. And but what happens is this can be handled. You can, I mean, the support can be the statement become more complicated, and the equalities become more complicated. But you can do it. I mean, it's just a matter of technical aptitude. It's not anything really deep. But what happens is this: one, you understand connected component and things like that. This is exactly the key geometric ingredient in the proof of the fundamental lemma. So that I cannot develop this point because it's a very long story to connect these pictures of integrable systems and the Langlands program. So I just avoid this. I just want to focus myself to explain you why you can prove this support F1 to S this for abelian fibrations. No. Do I have to stop? How many? Can I have more 5 minutes? It's okay. Okay, so which I first is to prove some kind of upper bound on the codimension of the support, as in the Goes-schema-Fashion inequalities. So let Z to be a subscheme of S, and then we define D delta of Z to be the minimum of delta on S. So this is the bound that is rich on dense open subset of Z. And we prove that the inequalities, we prove that the codimension, if Z is in support of F, support of some simple perverse sheaf occurring in the direct image, then the codimension of Z has to be no greater than delta of Z. And if moreover the geometric fibers are irreducible, then have strict inequalities. And now if you compare with the delta regularities, you just get Z equal to S. So the point is to prove this. And you can observe that this is just improvement of Goes-schema-Fashion inequalities. In Goes-schema-Fashion, this is D. This is dimension of P. And here you prove that is delta. That is very sensible because we believe that the abelian part do no harm. The abelian part is very smooth. The only thing that can do harm is either a file part, that's is delta. So this must be true. The point is how to prove it. So let me explain why this is true, right? The explanation of this inequality. So let me choose some point S so that this delta is your delta Z, and let me write down this Chevalier X extension. So P of S extends abelian varieties by F5 groups. And I assume that there is a neighborhood S prime S, some kind of small neighborhood if you wish, in complex. So first I assume that I have splitting from AS to PS to split the exact sequence. So this may not exist, but many times it exists. So this is not so serious assumption, but now I make a very serious and somewhat impossible assumption that I can spread this out. So I make a neighborhood, and I can spread my abelian scheme A prime to S prime, and I can lift A prime to P prime, extend this splitting. And if I can do this, I'm done. Because A prime can be lifted into P, A prime act on M prime, right? P act on M, I can leave abelian scheme into P, let it act on M, and because the stabilizer is a phi, it's actually almost free. Only have finite stabilizers, almost free stabilizers. And so that's why I can factor the map M prime, M to S to M, go to M mod A, and then to S. And now you see that we are almost done because the first map is smooth and proper because it's just a quotient by some abelian scheme. So we fit into the first case, and the second map is a relative independent delta. Then you can apply the Gauss-Schema fraction theorem. And then you believe that it should work. But now you get into troubles because in general that's something you're not satisfied. There is no way to spread this abelian variety. There is too many ways to spread the abelian varieties out, and there is no way to lift. Because usually the P is irreducible abelian varieties. You cannot have any sub-abelian varieties to put it. And here that's why you have to work really hard, but the basic argument is to overcome it, you have to redo on the argument in homological algebras instead of with geometry, with torus. You have to translate on this argument into homological algebras. And it takes a couple of pages, 50 pages of homological algebras, but you can do it. Well, let me stop here. Thank you very much for your attention.
Are there any questions, any comments? No one?
So I should explain proof in a plenary talk. So.
Okay. So let's thanks to Joe.